Hello and welcome to this clip on the chemistry of alkenes. It's the second out of two clips I've done. First clip was on naming and drawing and isomerism. This one is about the chemistry. As you can see, there's quite a lot it's going to cover, so I'll be as brief as I can, but try and focus on the key details that you need to know. So, as with any slightly larger topic, there's several definitions that you must have, so I'm going to bring them up, and please make sure you've either got flashcards for them and you've learnt them off by heart, because I'll assume that you know what I'm talking about when I mention them during my explanations. So whilst this clip runs, make sure that you've got these down on flashcards and that you're familiar with them, because the clip will assume that you are as it runs. Okay, so it's a fairly straightforward idea. You get the carbon atoms that have p orbitals above and below them. This allows the p orbitals to overlap, and as they overlap sideways, it's very important you say that there's a sideways overlap, and that creates a pi bond as well as a sigma bond. So the pi bond is one part of the double bond, the sigma bond is the other part. So a sigma bond is effectively the same as a normal single bond. So I've added a couple of annotations to the diagram to help explain a little bit what that means. So number one, make sure that you say that the p orbitals overlap sideways. You can draw it like this to get your full 2 marks. And the sigma bond is created when s orbitals overlap head-on. So this is your electrophilic addition mechanism. It usually gets you about 3 or 4 marks in a paper. You'll notice that there's actually 2 very similar versions of the same thing. The one at the top is the reaction between a halogen and the carbon-carbon double bond. So you'll notice it says that the chlorine-chlorine bond becomes polar. So I just want to explain a little bit about that. So you'll notice that the mechanism at the bottom is not complete yet. I'm going to bring in a picture that completes it for us. I just wanted to say a word about the idea about the chlorine becoming polar. So as the chlorine molecule approaches the electron-rich carbon-carbon double bond, what happens is the bonding pair of electrons is repelled away, as in this direction, so that makes one of the chlorines delta plus and the other chlorine delta minus. So what happens is a dipole is induced, so you have to draw in the dipoles quite clearly when you're doing this. So the next thing to happen is you've got I'm looking at the bottom one now, you've got a carbocation that's been formed. You'll see that the hydrogen in red is basically the one that came from the hydrogen bromide. So now you've got your bromine or your bromide. You need to draw an arrow from one of the lone pairs, curly arrow, towards the positive carbon. That's essential to get that mark. So what that means is that bromide ion attacks the positively charged carbon on the carbocation, and that creates a structure called bromoethane. So I'm going to stick to the colour coding that the image has. So you can see where everything ends up. So I'm going to annotate in red the key points you must do on either one of these types of mechanisms. They're both the same mechanism, it's just the electrophile is slightly different. So just to show you what I mean by the electrophile, chlorine is the electrophile in the first one, and hydrogen bromide is the electrophile in the second one. So I've put a checklist of things that you need to do at the bottom to make sure you get all the marks. Sometimes it might be 2 of them at the same time to get 1 mark. So I'm going to colour code each of them, the different coloured tick, and then I'm going to show the tick on each mechanism. So the first tick is in purple. The second tick is in magenta. You might call it red, but I'm going to call it magenta. The third tick is in brown. The fourth tick is in blue. So to do this one down here, I have to draw it in one more time. And the final one, we'll do that in black. So make sure you follow all of those points when you're doing this mechanism. That way you'll get full marks. Okay, so now let's have a look at something called Markownikoff's rule, which is to do with this mechanism, but it applies to what we call asymmetric alkenes. The two you see here, ethene, they are a symmetric alkene. So you'll see that propene is an asymmetric alkene compared to ethene. And instead of one product being made, you get two products, one being what we call a minor product, and one being called a major product. And what this has to do with is the carbocation that was formed in this process. So when you look at the carbocations at the bottom, you'll see that the primary carbocation is the least stable, and the tertiary carbocation is the most stable. So why is this? Well, if you focus on where the carbon is actually located, I'm going to make the image a bit bigger, like so. You'll see that you have one alkyl group, or carbon-based group, there. That's attached, sorry, beg your pardon, it's not like that, it's this one here. On the second one, you've got two alkyl groups, one hydrogen. And on the third one, you have three alkyl groups in total, and no hydrogens. The more alkyl groups you have, the more stable the carbocation is. When I say alkyl groups, they're carbon-based groups attached directly to the carbon that's positively charged. So the exact chemical reason behind this you don't need to know for A level. It's due to something called induction, or the inductive effect. You may come across it when you do A2, but in A1 most definitely you don't need to know about that. It's just the presence and the positioning of the alkyl groups. So if we go to our structure at the top, I'm circling the alkyl groups, and the structure at the bottom, I'm circling the alkyl group. So therefore we can now classify and explain why one is formed as a major product and one is formed as a minor product. Okay, so like I said, this only applies to asymmetric alkenes, not symmetric ones. So now it's time to go and have a quick look at the test for the carbon-carbon double bond. Now we've looked at the electrophilic addition to the carbon-carbon double bond. So you may well have done this one at GCSE. The chemistry of it's no different. We can see from this photograph and the information that's been given to us that sunflower oil and peanut oil are unsaturated, but coconut oil is not. So it's a very simple diagnostic test. It's important when you're talking about this in exam questions that you mention that it's decolorized. In other words, there's a reason I've highlighted it here. It's important for exam questions to say that bromine is decolorized if you asked it to observe or say what you will observe. Okay, so let's now have a quick look at the reactions of alkenes that you need to know about. So at this point it might be worth getting a plain piece of paper and copying this down and going away and learning it. In other words, you need to be able to reproduce this pretty much as it stands in front of you. Now obviously we've got propene, so you might want to note that propene as an asymmetric alkene produces mixtures of structural isomers when you've got HBr or H2O. So I'm just going to annotate each part of this so you know what the type of reaction actually is. So bromination and chlorination are both examples of halogenation, but there's a little bit more to it than just that. So we call it dibromination or dichlorination or dihalogenation because you're putting two halogen atoms onto the carbon-carbon double bond. So the carbon-carbon double bond would obviously have been here and here. You can see that clearly. So you've got dibromination, dichlorination, hydration, which is addition of water, or hydrogenation, which is addition of hydrogen, and monobromination or monohalogenation. So the next thing to consider when looking at alkenes is polymerisation. So we call this addition polymerisation because it's an addition of monomers to each other. So I just wanted to focus on what a repeat unit was. I asked you to make sure you knew what that was in the list of definitions at the beginning of the clip. So you can see from that diagram that your monomer is ethene and your polymer will be called polyethene, and the repeating unit is the same thing that's repeated over and over again. So the N value refers to a very large number, usually between about 5 or 10 or 20,000, something like that. So this one's an animation showing how but-2-ene comes together to form lots and lots of but-2-ene repeat units. What you might want to do is have a look at it and then see if you can work out what the repeat unit for but-2-ene is. Pause it when you've had a look at it, go through its cycle a couple of times, and then see if you can draw it. Then pause the video and come back. So I always start by doing the square brackets. You can do curved brackets if you want, and put an N outside. I then draw the trailing bonds, as we call them, and then what you do is you think to yourself, okay, where does the carbon chain, or how many carbons are there in the carbon chain? So what you do is you put, I'm going to do it in a different colour just to make it clear, you put what was the carbon-carbon double bond in the middle, but it was but-2-ene, wasn't it? So that would have been carbon number 2. So that must mean that there is carbon number 1, which is there, and carbon number 4, which is there. Obviously you'll have hydrogens as well. Okay, so that's called a repeating unit, and many, many, many of them will go together in a long, long chain to make polybut-2-ene. So here are some other common monomers and the polymers you get from them. I apologise that this particular image doesn't have the 120-degree bond angle in the alkene monomer that it should have, but you take what you can get, I guess. Okay, so I just want to spend a couple of minutes talking about some of the problems with disposal of addition polymers, because the polymers themselves are very, very stable, so they don't break down in the environment very well. So, if we have a think about those two problems, they're quite difficult to deal with, really. If it's non-biodegradable, that means it doesn't break down in landfill. And often if you burn these things, you can get toxic fumes given off. So some examples of the toxic fumes I can put over next to each of the polymers concerned. So we have to be very, very careful in dealing with them. So how do we get around this problem? So there are two possible solutions. You could recycle them by sorting them out and then remold them into new things, so new products made from the same material. You could use it as a chemical feedstock, meaning a starter material to make other things. And finally, if it's non-toxic to burn, you can use the energy. Okay, so that comes to the end of our sort of quick tour of alkenes. I'm not going to go through any particular exam questions because there's far too many to choose from. The best thing to do, if you want some practice, is to go to your textbook, find some end of chapter questions, and maybe make a note of the specific part of alkenes that you've struggled with. It might be the mechanism, it might be the reactions, you find it hard to remember them, it might be polymerisation. It doesn't really matter, provided you go and find questions on that particular area, try them out, bring them to your teacher if you get stuck, or maybe a subject extension. But in the meantime, I hope you found this useful, just as a review perhaps, or a quick look ahead to alkenes. And all the best, and thanks for listening.